thank you, Viviana, for the introduction. So, yeah, today we will go a little bit into the details of these charged particles that were mentioned several times in the school. So, with cosmic particles that we call cosmic rays that are closely connected to dark matter searches and are responsible for much of the gamma ray emission we see from the galaxy. So it's worth studying them in more detail. Actually, let me recap a little bit. So what we learned so far, we learned that dark matter is up there, that we learned something about the WIMP paradigm, and we learned that these hypothetical particles have several properties. They should be massive, neutral, and stable, very long-lived, feebly interacting, and are supposed to annihilate or decay into standard model particles. So it's very natural to, so we have a very natural interplay between the study of the charged cosmic particles that are out there in the galaxy and hypothetical particles that should originate from wind. So that's why this connection between dark matter and dark searches and cosmic rays is so natural. But I will try also to convince you that cosmic rays are really an important field of research per se. It's central in high energy astrophysics and has a lot of interesting questions that are interesting to study. So we'll try to convince you about this. And actually, yeah, one of the challenges we will see is to disentangle the signal associated to these particles originating from astrophysical sources to a potential exotic signal, as was mentioned several times in the school, also by Gabi and other speakers. So yeah, let's learn more about cosmic rays. So we know about these particles. So we have known about these particles for a long time. So typically we mention Victor Hess as the discoverer of cosmic rays in 1912, but actually there were several experiments at that time, so more than 1 century ago, that typically measured either the decrease of the ionization level in the atmosphere, in the water with increasing depth, or the increase of the ionization level in the atmosphere with increasing height. So measuring how the ionization of the atmosphere and of the water changed with height and depth, people realized that there was some kind of penetrating ionizing radiation coming from above, from the sky. So that was noticed very early on by several experiments, Domenico Pacini, Victor Hess, also Theodore Wolff, and others. And nowadays we study them with in a lot of detail. I mean, we measure them depending on their energy. We measure them with different techniques. So in the GeV-TeV range, we typically study and measure this particle with space-based experiments, like, for example, the AMS experiments, which is on board the ISS, the International Space Station, at extremely high energies. We typically study them with ground-based experiments that measure indirectly the cosmic rays by detecting the air shower that is generated in the atmosphere when the cosmic ray hits the atmosphere. And the properties of cosmic rays are typically captured by this very nice plot. So you see, they first of all they constitute an isotropic flux coming from outer space. It's air from all directions, and you can notice the huge energy span, the huge energy range that is covered. So more than 11 decades in energy, up to really extreme energy, 10 to the 20 electron volts. Typically mentioned that these energies are far higher than the ones that we can reach with particle accelerator at Earth. And the largest energies are actually microscopic energy. So it's really remarkable to have a kinetic energy of several joules, which is a typical energy of a macroscopic object, or tennis ball, or something like this, concentrated in one single particle. So you go to extreme energies and to an extremely relativistic domain. So Lorentz factors are as large as 10 to the 11 or more. And these particles follow a non-thermal spectrum. So typically power law in momentum or in rigidity, and you see that the fluxes go down significantly from few particles per centimeter square per second, GeV, down to very low fluxes of few particles per kilometer square per year at extremely high energy like EV or so. And yeah, so some properties of this flux. So typically, yeah, we study the all particle spectrum. We typically mention that it's consistent, that the spectrum of the all particle spectrum is consistent with a single power law, with a slope around e to the minus 2.7 in a quite wide energy range from the GeV up to the sort of PV energy or so. But yeah, let me mention that if you zoom in a little bit and with the increased accuracy of the data, we start to notice some spectral features. So for example, AMS detected a hardening, a progressive hardening around 200 GeV, and actually going to higher energies and looking at the DAMPE data and also other data from other space missions, you can start to see, for example, a spectral bump centered at 10 TeV. So we start to see features on top of this power law, which could be very relevant. Actually, a lot of physics can be done with these features. For example, this could be signatures or of some nearby accelerator, like popping up from the sea of cosmic rays. But we will see a little bit of this later. So just let me mention that we start to see structures and a little bit more of a complicated structure in the all particle cosmic ray spectrum, and we expect to see more and more features that are very interesting to investigate. And then, yeah, a very relevant feature actually that has been known for a long time is actually located at few PV, and it's called the knee. The knee is a relevant steepening of the spectrum, and it also corresponds to a change in composition. So below the knee, the all particle spectrum is largely dominated by protons, while above the knee you see more and more presence of heavier elements, and you see a steepening of the spectrum. So one of the interpretation of this feature is that the knee should correspond to a sudden drop of efficiency in the acceleration of particles in the galactic sources, in the galactic environment. And maybe we'll see it a little bit more, but the reason why you first have a proton-dominated component and then you see more and more heavier particles is that the cutoff, the maximum energy of acceleration is actually a function of rigidity. So the main quantity that dominates cosmic ray interactions is the rigidity, which is the momentum divided by Z, by the atomic charge. So if you plot the spectra in energy, you would see the maximum energy translated and at larger and larger energies, given the rigidity of a reference rigidity of few GeV. So you would see the cutoff of protons at, for example, 2 or 3 GeV, the cutoff of helium at twice as much, because the atomic charge of helium is double, and so on. So basically, above the knee, you see one after the other the drop of efficiency of heavier and heavier particles corresponding to the same rigidity of few PV. So this is the sort of most natural and common interpretation of the knee. There are others, but we think that this is really where particles stop being accelerated efficiently in the galaxy. And actually, another thing that happens is then you have another feature. You have actually a hardening at energies that are way larger. This is called the ankle. It's another very important feature. It occurs at even higher energies, around 5,000 PV. So we call this EV. We have to use even more prefixes for these extreme energies. And here, somewhere around the ankle, there should be the emergence of the extragalactic component of the cosmic rays. So this is actually something that you can think about by yourself. So every now and then I will pop up some questions that you can think about and you can work out by yourself. And of course, we can also discuss them later in the other town if you want, or you can contact me during the school. So, for example, one idea about the ankle. Okay, the main idea about the ankle is that you start to have the emergence of the extragalactic component of cosmic rays, and so one may wonder, how can we prove this with a very tiny order of magnitude computation? And actually, the question is, so how can we convince ourselves that the cosmic rays can stay and be confined in the galaxy up to this energy, and they cannot be confined in the galaxy at larger energies, at energies larger than the ankle? We will also discuss a little bit more about the concept of confinement, but the idea is that the galaxy is filled with the magnetic field, and the magnetic field is able to trap these charged particles, but this cannot happen at all energies. So you can just work out the numbers for yourself, and you see that the key quantity. Now, for this question in particular, I will give you a little hint, but it's very easy. So you can actually think that the key point here is to think in terms of the Larmor radius of a charged particle in a magnetic field, and work out the number, and compare the Larmor radius of the magnetic of a charged particle in a magnetic field with the typical scale height of the galaxy, of the galactic diffuse halo. So I think this is a nice little exercise with numbers that you can work out, and it will become a bit clearer in a while when I will tell a bit more about cosmic ray confinement. But for now, the flash is that the take-home message is that the galaxy and the magnetic field in the galaxy is able to confine charged particles up to energies around the ankle. So somewhere around the ankle, you should see a new population, a harder actual population popping up in the all particle spectrum, possibly of extragalactic origin. And actually, yeah, the story is more complicated than this. I will not go into the details, but the study of the high energy part, or the extremely high energy part, is very complex. So it's very important to study both the spectral features and the composition from the knee to the ankle. And this is done, for example, by these large experiments like the Pierre Auger telescope, Cascade Grande, LASO, and other similar experiments that really are able to reconstruct the shower of secondary particles originating from these extremely high energy cosmic rays, and measure energy and basically measure the nature of the particles, so measure the composition. And so there is more and more knowledge about how the different components of the cosmic ray spectrum, so the protons and the other nuclei, show and feature spectral breaks at different energies. So we start to see, for example, that the proton really has a steepening around the energy of the knee, and all the other nuclei, in particular the heavier nuclei, show this steepening at larger and larger energies up to what is called the second knee. And then we start to see again a change of composition and a change in spectrum at the ankle, where probably a new component associated to extragalactic cosmic rays is kicking in and start to dominate the extremely high energy part of the spectrum. So this is still a field of research, let's say, under development, and there's a lot to do in this field. For example, the exact location of the transition between knee and ankle, between galactic and extragalactic, is still not super clear. And also there are hypotheses about a second galactic component that may dominate between second knee and ankle. So possibly different classes of sources that appear at very, very high energy. So this is a very active field of research, and the understanding of the nature of cosmic rays between knee and ankle is still, I would say, an open problem. Yeah, a little bit more about composition. So let's be a little bit more quantitative. So I mentioned the all particle spectrum, but actually in cosmic rays, you see all the nuclei, basically, all the nuclei are represented. The vast majority of these nuclei are protons, 90% of them. Then we have helium, and then we have all the heavier species. And it's very important to point out that the light elements, lithium, beryllium, and boron, are overabundant in cosmic rays with respect to the solar system abundance. It's like 5-7 orders of magnitude. Actually, all the lithium and boron that we have in the universe is basically produced by nuclear processes involving cosmic rays. So it's all related to processes associated to cosmic rays, and we will cover this a little bit later. For now, let's just have this information. And then we also have leptons in cosmic rays. So we don't only have protons, we have electrons, and we have antiparticles. So there's really a very large spectrum of particles, and the protons really dominate the flux. But it's very, very important to mention that there are leptons, like electrons in particular, and then we have antiparticles in the flux. So both positrons and antiprotons. And these are, as we will see, are very important for dark matter search, as we will see in a while. There's also an ongoing search for antideuteron, antihelium, so antinuclei. That would be very, very interesting, very important for dark matter searches. And so, yeah, let's start with a little bit of physics about. So we have described a little bit the features, the properties of the cosmic ray flux, and what is that we are studying about the physics of these particles. So yeah, we're mainly dealing with two big questions, and we've been dealing with those questions for really decades. So the first is, where do they come from? So what are the main sources of cosmic rays? In particular, in the GV, TV region, this refers to galactic sources, and I will mostly cover this the galactic environment in this talk. And how can they reach this very large energy? So how come that some astrophysical objects are able to accelerate particles up to PV energies or even more in the galaxy, and even more extreme energies in other environments, astrological environments? And then another question is, how do they propagate in the interstellar space when they are released from the source and they reach us after a long journey through the galaxy? So how does this work? How come they are confined? How does confinement work? What is the microphysics behind this process? And this is very interdisciplinary because it requires a lot of knowledge about plasma physics. So most of these questions deal with the interplay with the physics of turbulence and magnetohydrodynamic turbulence in the galaxy. So that's a very complicated topic, and I will try to give a glimpse of this of the key concepts about this issue. And actually, we know some answers. I mean, we have built over time. People have built over time a sort of standard picture of how these things work, and this, let's say, orthodox picture is based on two main pillars. So the first pillar deals with the sources. So we believe, many scientists believe, that the bulk of the energy of these cosmic particles originate from supernova explosions in the galactic disk, although other sources might be at work. So there's kind of an agreement that supernova, actually the shocks propagating after a supernova explosion in what is called a supernova remnant, is responsible for the acceleration of these particles and provide the energy budget that is associated to these particles. However, other sources might be at work, and there's been a lot of debate about, for example, the role of pulsars, or the role of completely different objects, such as, for example, X-ray binaries that are compact objects like neutron star black holes that are accreting matter from a companion star and are able to emit a jet, which is in turn able to accelerate particles. So there are many sources at work, but really, because of energy budget arguments, as we'll see in a while, we believe that the supernovae are the most important player in this field. And we have a theory about that. So over the years, many scientists have developed a theory called diffusive shock acceleration that is able to describe some key features of cosmic ray acceleration. So why it produces, for example, a power law spectrum, and it's a very convincing theory that I will explain at least in the very key concept in a while. So yeah, this is more or less the first fact. So we believe that every now and then a supernova explodes in the galactic disk, actually a few times per century. Then a shock is propagated in the interstellar medium, and this shock is able to accelerate cosmic particles with this process called diffusive shock acceleration. And yeah, you see here on the right a nice picture of a supernova remnant. And yeah, the other pillar, the other main idea refers to transport. So the other key concept of cosmic ray physics is that cosmic rays are, when they are released from their sources, they stay in the galaxy for quite a long time, order of tens of mega year, and they're actually diffusively confined within an extended, wide, magnetized halo, galactic halo. So, okay, there are a lot of concepts here. So there is a confinement, so cosmic rays don't travel straight lines and exit the galaxy like ballistically, but they undergo a random walk, which is described by a diffusion equation. And this random walk occurs because of the presence of a wide magnetized halo that is also turbulent, and the turbulence is the key reason why the particles are scattered many times and in a random way and undergo a random walk. And this is quite extended and quite wide, and you can actually see it. I mean, for example, looking at the radio emission from the galaxy, the radio emission from the galaxy in some frequencies, for example, here you can see the famous Haslam map at 408 megahertz, is really dominated by synchrotron emission that really traces where, in this case, cosmic ray leptons are and where they interact and how they interact with the magnetic field. So you can really see an extended bright emission from the galactic plane that is really tracing where cosmic rays are confined. So you really can see this by looking at, for example, the radio map of the galaxy. But actually, if you look at the multi-wavelength emission from the radio all the way up to gamma rays, you see the imprint of this magnetized galactic halo that confines cosmic rays. So yeah, these are more or less the two key concepts, and we can start analyzing the first one. So yeah, I try to convince you that that cosmic rays are actually accelerated by supernova remnants, and this was realized very early on. Actually, there's a nice paper in the 30s by Fritz Zwicky and Bade. Zwicky is the same guy that made a very important contribution to dark matter, to the discovery of the dark matter. So he was extremely bright and extremely active in that period. And they wrote this very nice proceeding with a one-line abstract, claiming that the hypothesis that supernova emit cosmic rays is in reasonable agreement with cosmic ray observation. That was a very nice idea. And you see how you write a one-line abstract, and after 1 century, people still talk about it, almost 1 century. So actually, they had the right idea, but not in the right context. So they were not really thinking about supernovae in our own galaxy. Now we know that this energy budget argument really refers to the supernovae in our own galaxy. So the key concept here, and I really suggest you to work out the numbers by yourself, because it's I think a nice exercise that is very useful. So the key concept here is that if you can compare basically two quantities, right? On the one hand, the energy density in cosmic rays, actually the flux associated to cosmic rays, and there are some useful numbers here. So the cosmic ray energy density is of the order of 1 electron volt per centimeter cube, and then you know also the residence time of cosmic rays is order of 10 mega year, and so you can knowing also the volume of the galaxy, you can work out a flux, a rate associated to the cosmic rays as an energy per volume per time. And if you compare it with the supernova, with the energy, with the rate of energy injection from supernovae, you can see that the two energy budgets are compatible. So assuming an efficiency of a few percent, so assuming that supernova explosion somehow, for now we don't know how, but if we assume that somehow supernova explosions are able to convert a few percent of their kinetic of the kinetic energy that is released into and to convert it into acceleration of particles, and if you take into account that supernovae occur in the galactic disk at a rate of few percentuary in our galaxy, if you know the energy budget of a supernova, so you can work out by yourself the energy associated, the energy budget, the energy injection rate associated to supernovae. And you can see that assuming just a few percent efficiency in cosmic ray acceleration, this number is compatible with the flux, with the total overall flux associated to cosmic rays in the galaxy. So this is a very convincing argument, because there are not so many, I mean, this energy is huge, so there's a huge flux in cosmic rays in the galaxy, and there are not so many energetic events that can be responsible for that. I mean, if you work out the energy budget for other very energetic events, you don't reach these numbers. So it's very natural to think of supernova remnants as the main candidates. And yeah, just let me say a few words more about just in case I mean someone is interested about this object. So these objects are really key, are really of key importance in cosmic ray physics, and they are structures resulting from explosions of supernovae. The energy released is, as I mentioned, extremely large, of the order of 10 to the 53 erg, and actually most of this energy is released into neutrinos. So 1% of this energy, around 10 to the 51 erg, is actually released in kinetic energy. And we assume that 10% of this energy in turn is destined to cosmic ray acceleration. And the key feature of this supernova explosion is that a shock, so a shock means a discontinuity in density and pressure that travels in the interstellar medium, expands after the explosion at very large speed, like thousands of kilometers per second, at least in the first phase, and then yeah, there is a progressive slowing down of this shock. But and this shock is traveling and is expanding for quite a long time, tens of kilo a year. You see, it's very fast, but still non-relativistic. So we are way below the speed of light, and the presence of this non-relativistic spherically symmetric shock is the key for the process of cosmic ray acceleration. So yeah, I think yeah, there's plenty of time. So I would like to tell you a little bit more about how this acceleration process works. So yeah, as I mentioned, the key object is this shock. So if you imagine that you are sitting on this shock front that is traveling, expanding in the interstellar medium, you basically see a wind of interstellar gas coming in your direction. This is the so-called upstream medium, and then this wind of gas, interstellar gas, crosses the shock and is heated and compressed by the shock. Basically, the shock works as a very efficient heating and compressing machine. And so the flux that is behind you, if you're sitting on the shock, so in what is called the downstream region, the one at the right in this plot, is actually hotter and denser. And this gas that is arriving towards you and then is traveling downstream is also turbulent. So it is also turbulent and magnetized, like all the interstellar gas we have has these two properties. So it's typically magnetized and is typically turbulent. And this is key in accelerating cosmic rays. I will see why. And the mechanism is called diffusive shock acceleration, which ironically, I mean, it's also called Fermi first order acceleration. It was not really proposed by Fermi, so it's fine to call it Fermi first order acceleration because it's the evolution of a previous idea by Fermi, but the application of this idea to this peculiar environment, a supernova shock in this particular way, was actually developed in the late 70s by Tony Bell. These people that you see here, Tony Bell, Bransford, Stryker, Oxford, and Krinsky in the late 70s, and these are the people that have to be also really credited for this theory, the theory of diffusive shock acceleration. And basically, I will not go through the full computation, the standard computation that you find in all textbooks, but I will try to give you like an intuitive picture of this process. So how does it work? I mean, so you have some particles that cross the shock, and here they interact with the turbulent downstream medium, and everything can happen, right? It's a turbulent medium, so you have a magnetic field, so the particle can be deflected in any direction. So if you are in the reference frame of the downstream medium, the charged particle will conserve its energy, but will be deflected in a random way. And some lucky particles, there's a chance, there's a given probability that the particle has actually flips its velocity, so is basically sent back to the shock and crosses the shock again. So this is the key process of diffusive shock acceleration. So some particles actually cross the shock, you see from left to right, so from upstream to downstream. You see the scheme here. They arrive downstream. Here there's turbulence, their velocity is flipped in a random way. There's some chance that the velocity is flipped in the opposite direction and the particle crosses the shock again. In doing this, okay, this is tricky, right? Because if you see the process in the reference frame of the downstream medium, then there's no energy change, right? Because it's just a magnetic field. It just changes the velocity, but it doesn't change the modulus of it just changes the direction, but not the modulus of the velocity. But if you see it from outside, from the lab frame, from an outside observer, what happens is when the particle recrosses the shock, it gains energy because it brings the velocity of the downstream medium on top of the initial velocity, basically. So if you see it non-relativistically, it's really u plus v, where v is the velocity of the particle and u is the velocity of the shock. Of course, the problem has to be treated relativistically, and you have to perform two boosts to change of reference frame, but the result will not change. I mean, the result is that when you have this lucky process of crossing the shock, velocity flip, and recrossing the shock, you gain energy with, and the amount of energy you gain is actually linear in the shock velocity. So the delta U over E per acceleration cycle, this is called an acceleration cycle, is actually linear, is proportional to the shock velocity. So the shock velocity divided by, so the delta U over E is basically proportional to U over C, where C is the speed of light. And you see that this process can be iterated. So every time there is a finite probability to be lucky, so to be flipped in such a way that you return to the shock. And of course, you can be unlucky. I mean, you can always the particle can be lost downstream. So actually, only a very small number of lucky particles will go through several acceleration cycles and will actually get to the highest energy. So that's also why eventually power low spectrum with a very limited and little number of highly energetic particles is created. So yeah, this is the key idea of diffusive shock acceleration. Are there any questions? Because I think I'm not sure if I see the chart. Let me check. Are there any questions?
Yes, Daniel, actually there is a question on the chat.
Yeah, here it is.
Can you hear it, or you want
I can see. Does the process depend on the relationship between the disturbance of B and the background B. Oh yes, yes. Yeah, this will be clarified yeah, a bit later, but yes, actually when a charged particle interact with a turbulent magnetic field, so the charged particle with the given Larmor radius is actually sensitive to the disturbances of B that so basically the waves in the plasma that have the same wavelength as the Larmor radius of the particle. And yes, the amount of I mean the process depends on how much power is stored in the magnetodynamic waves of the same wavelength of the Larmor radius of the particle. So yes, and I will cover this. I will cover this later when we talk about transport. So we will go back to that. Yeah. And yeah, another question. So okay, so just let me mention that this process is well, doesn't last forever. I mean, there is a maximal energy that you can get, and yeah, maybe yeah. If there are other questions, if you can maybe pop. I mean, just shout at me because I think I cannot. I have some problems in checking the chat sometime, so it's slowly responding. Anyway, so yeah, the maximal energy. So there is a maximal energy. So I mean, you can't go on with this acceleration process up to arbitrarily high energies. And the reason is that in order for this process to work, you have to keep confined the particles close to the shock. So typically, yeah, I don't know what's happening here. Okay, yes, yeah, I can. Oh, now I can see the chat. Okay, yes, cool. So yeah, the maximal energy can be computed by this in a general way with this simple Hillas criterion. So again, you have you have to compare two different orders of magnitude. On the one hand, the sides are S of the acceleration region. On the other hand, the sides where the cosmic rays of the region where cosmic rays diffuse close to the shock, which is d over v of the shock, where d is the diffusion coefficient. And you end up with this very simple expression of Emax, which is linearly scaling with the radius, with the sides of the region, with the velocity of the shock, and with the magnetic field near the shock. And this is intuitive, right? So the larger the source is, the more you are able to confine within the close to the shock more and more energetic particles. And then the more intense the magnetic field is, again, the more you're able to deflect and keep particles trapped close to the shock, and same for the velocity. So you have this very nice criterion for the maximum energy that for merely geometric reason you can attain with this process of diffusive shock acceleration. And if you work out the numbers, you can see that with appropriate amplification of the magnetic field with respect to the standard micro-Gauss value that is typical of the interstellar medium, with appropriate amplification of the field near the shock, you can get energies in a supernova remnants that are as large as PV. So you can get to there. But I mean, in order for this process to happen up to PV energies, a very key point is that you need a quite significant magnetic field, a quite larger, a magnetic field which is significantly larger than the micro-Gauss, so amplified by 2 or 3 or more orders of magnitude. So, and one of the theoretical challenges in the field is how to understand and how to explain this magnetic field amplification. But still, I mean, the current knowledge is that in our own galaxy, the properties of supernova remnants are such that you can attain, you can get energies as large as PV, and this maximum energy can be computed and summarized with this very nice and clean formula as a function of the size of the acceleration region, the velocity of the shock itself, and the intensity of the magnetic field. So sorry, here in this slide, the Emax, I think there is, yeah, it's in TV. So in this expression here, if RS is the order of parsec, US is the order of 1000 kilometers per second, and BS is of the order of 1 micro-Gauss, you get an energy of 1 TeV. So with the field amplification of 3 orders of magnitude with respect to the micro Gauss reference level, you can get from TeV to PV energy of maximum energy. Yeah, so that was, I think, enough for cosmic ray acceleration. There are several other topics that I would like to cover, but I think, yeah, we have still plenty of time. So, yeah, I would like to talk a little bit about this confinement process. So it's really very important. So we mentioned that cosmic rays, cosmic particles are diffusively confined in the galactic halo, and there are several pieces of evidence for this process of cosmic ray confinement. So first of all, the isotropy itself of the arrival direction. So we know that cosmic rays arrive at Earth from all directions with a level of isotropy of the order 1 per mil. So there's no privileged direction. And so, you know, even in near, you can pinpoint directly to sources. So something has to go on. Something has to happen between the nearby accelerators that we know exist and we know that are supposed to accelerate cosmic particles and us. Otherwise, you would really spot some bright regions in the sky where cosmic particles arrive way more than compared with other directions. Instead, we have really everything is mixed up and everything is isotropic. And then we see this bright diffuse emission, which is very wide and bright and homogeneous from radio, and in particular in gamma rays. We see it very well with Fermi, as Michael and Gabi and other speakers mentioned several times. We see this very bright and nice diffuse emission in gamma rays that is the signature of the presence of a cosmic ray diffuse sea in our galaxy. And then we have an overabundance of light elements, as I mentioned. So lithium, beryllium, and boron were produced in negligible or almost null quantity during the Big Bang nucleosynthesis. They're not produced in stars. So, and the reason why they are so abundant in cosmic rays is compatible with a picture in which cosmic rays are the primary cosmic rays. So, for example, protons and heavy nuclei are accelerated in supernova remnants, and then they wander around the galaxy for a very long time, or the tens of mega years. They interact with interstellar gas, and the heavier species, for example, carbon, nitrogen, and others, and oxygen, that are very abundant as well, produce lighter ones, in particular these lighter species that are supposed to be produced in very small quantities in other processes like lithium, beryllium, and boron via spallation. So basically a nuclear interaction with the protons and the helium nuclei that constitute interstellar gas. So the overabundance of these lighter species, lithium, beryllium, and boron, is compatible with a picture in which cosmic rays are trapped in the galaxy for a long time, for tens of mega years, and a picture in which heavier particles produce the lighter ones via a process called spallation. And this is more or less the geometry of the problem. This is the usual way to visualize this problem. So you imagine the galaxy as, you know, this cylinder, and you have a disk, a tiny disk with a scale height of like 100 parsec or so, where most of the acceleration of cosmic particles take place, where all the supernova explosion take place. And this is, yeah, very tiny. This is also where most of the star formation takes place, and where the astrophysical activity takes place, where you have star formation, you form supernovae, and you have acceleration. And then this disk is embedded in a larger magnetized halo of larger height of a few kiloparsec. Actually, we don't know what's the precise extension of this halo. We think it's at least a few kiloparsec. It could be as large as 10 or more. There are even some papers that hypothesize even larger of tens or even up to 100 kiloparsec halo. So we don't really know how much it extends, or do we know it exists? And the cosmic particles are really trapped in this magnetized halo for a long time, and they random walk through this magnetized halo, and then they leave the galaxy at some point when they reach the upper or lower boundary of this magnetized halo. And this is the key process that explains the formation of lithium, beryllium, and boron. You see here on the left a nice picture of a giant molecular cloud where a lot of gas is present. Most of the gas is actually located in the galactic disk. and heavy cosmic rays interact with the gas, with the interstellar gas, and produces lighter species. So typically, carbon, nitrogen, and oxygen, which are very abundant species, are supposed to produce via a chain of nuclear reactions, lithium, beryllium, boron, and other lighter species. And it's very nice that you can also compute, given the relative abundance of the secondary cosmic rays, the lighter species, and the primaries, and given the cross-section for this nuclear process called spallation, you can actually estimate the column density. So the column density is really the mass per area that is traversed by cosmic rays all across their journey. And it turns out to be a few grams per centimeter square. So over 10 mega year or so, the cosmic particles encounter interstellar gas with the total column density, accumulated column density, this is called grammage, of a few grams per centimeter square, which is roughly the grammage associated to, probably 100 or so of sheets, of normal sheets of paper, of printing paper. And this is much more than the column density associated to the galactic disk, because in 10 mega year, you have to cross the disk several times during this long journey to accumulate such a significant grammage. So you see, it's significant for cosmic rays, but eventually it's very small for lab standards. And this gives you an idea of also how diluted and the interstellar gas is, although the effects of this gas are so macroscopic on the abundance of cosmic rays and on the astrophysical processes. Yeah, and how does this process work? So in order to understand it, we have to know something about the galactic magnetic field. So we have to know that the galaxy is permeated with the magnetic field. And you have actually what is called the regular coherent magnetic field, which mainly follows the spiral arms, mainly located on the plane. Actually, there is also an out-of-plane component. So the structure, the topology is quite complex, but it is well studied in several papers like this one that is very interesting, and it is studied by measuring for example, the rotational polarization plane of faraway sources, polarized sources. But most importantly, you have a turbulent field. So in the galaxy is filled with a turbulent magnetic field, which is well described by superposition of magneto-hydrodynamic waves. And yeah, we'll not go very deep into the theory of that, but let me just recall that there are mainly two types of plasma waves. One is called Alfvén waves, the other is basically magnetosonic waves. So you can imagine the Alfvén waves as basically similar to the wave packets that travel on a guitar string. The only difference is that they actually travel on the magnetic field lines, and the restoring force is not the string tension, but is the magnetic tension. And so these are basically transverse waves that travel. So the displacement is perpendicular to the wave vector, and are called Alfvén waves. On the other hand, you have magnetosonic waves, which are closer, more similar to pressure waves. So these are longitudinal waves, and they can be represented as magnetic field lines that become dense and rarefied progressively when the wave packets travels in the magnetized interstellar medium. So you have these two types of waves, and these waves follow a turbulent cascade. So what happens is that basically larger waves with larger wavelength, transfer energy down to smaller and smaller waves, and eventually you end up with a very nice and broad power spectrum. So if you measure the energy stored in these magnetohydrodynamic waves at different scales, actually from very large scales, order of tens of parsecs, down to very small scales, order of astronomical unit or even less, you have this big power law in the sky that is very famous and spans again many orders of magnitude, and it follows very closely a power law. So the energy stored at different scales follows this very nice and regular scaling. Okay, so and then, okay, the next step is understand how a charged particle, a charged cosmic ray, interact with this turbulent field. And we have a theory for this. This is the so-called, what I call the second pillar, right, of this big picture of this big picture of cosmic rays physics. The second pillar is that the cosmic rays are confined in the galactic halo. They interact with the turbulent magnetic field, and the theory describing this process, at least at zeroth order, first order, is called the quasi-linear theory of pitch angle scattering. So yeah, this is again not very new. It was developed in the 60s. Basically, you can find here a couple of reference books. A very good one by historical one by Ginsburg and Sierowski from 64, and then another big classic is the Berezhinsky et al. Book called Astrophysics of Cosmic Rays from the 90s, where this theory is really explained in detail. Also, you may take a look at this review, more modern review, where also the key concept of this theory are explained. And yeah, so I will recap here basically the assumptions of the theory and the key result. So we are talking again about the interaction of a charged particle with the turbulent waves. In particular here, the assumption is that the main process is the scattering between Alfvénic waves and charged particles. And we also assume that Alfvén waves are isotropic, and their energy density is characterized by a power law spectrum as a function of the wave number k. So this is the first assumption. So you have to imagine an isotropic pattern of Alfvén wave packets of different wave number, random direction, random phase. And we also assume that at the scale of interest, and we will see a little bit what is the scale of interest. So at the scale of interest, these Alfvén waves, the inhomogeneities associated to these Alfvén waves are small with respect to the coherent large-scale magnetic field. So the delta B associated to the wave, to the perturbation, is small compared to the intensity of the coherent large-scale magnetic field, which I mentioned before. So we all the time we have to remember that in the galaxy we have this regular coherent large-scale structure called regular field, and on top of that we have these fluctuations that, and it's very important for this theory to work, since it's a quasi-linear theory, that at the scales of interest the fluctuations, the inhomogeneities, are small with respect to the regular field. And so the key result of this theory is that cosmic rays basically diffuse along the regular field. So first of all, let me say it's called a pitch angle scattering, because what happens is that a charged particle interacts with an Alfvén wave packet with some given angle, and basically the angle is randomly changed, and every time you interact with an Alfvén wave packet, the angle is changed randomly, and this is basically responsible for the particle to move randomly along the magnetic field line and to be scattered off back and forth randomly along the magnetic field line. And so, yeah, the first key result of quasi-linear theory of pitch angle scattering is that cosmic ray diffused mainly along the regular field. And the key properties, as you may have heard about the diffusive motion, is that at the average displacement delta x after time delta t is proportional to the square root of d times delta t. So a diffusive motion is basically different from a ballistic motion. It's a random walk, and the displacement, the average displacement, is proportional to the square root of time, with this diffusion coefficient as proportionality constant. It's also a resonant process, so that's what we were mentioning before. So the Alfvén wave packets that contribute to the process need to have a wavelength comparable with the gyro radius of the particle. And just to give you some numbers, so for example, a GV particle, a GV particle in a magnetic field of a few microgauss is expected to interact, given this resonant process, with inhomogeneities of the scale of few astronomical units. So GeV particles are really probing a very small inhomogeneities compared to the size of the galaxy, but still large. I mean, an astronomical unit is the distance between the sun and the Earth, so it's absolutely not negligible. And then another key result is that the parallel diffusion coefficient as a function of rigidity can be written in terms of the turbulent power at the resonant scale. So this is the sort of main formula. You see that this diffusion coefficient can be written in terms of this expression, where you have the power associated to the associated scale of reference at the denominator, this P of K res. And this can be actually recast in this way that you see below. So D is proportional to Larmor radius times velocity over this F function, which captures the basically turbulence strength at that scale. So intuitively, you see that this means that if at some given scale, you have a large power in your inhomogeneities, your P is very large, so you have a lot of wave packets, a lot of sine wave packets with a large amplitude. This results in a very low diffusion coefficient, which means a very high level of confinement. Given this expression above, I mean, if the diffusion coefficient is low, the cosmic rays are scattered so much, the scattering rate is so large that particles are very effectively confined. So a large power in magnetohydrodynamic fluctuation results in a lower diffusion coefficient, which means high confinement. That's the key result of this theory. Yeah, let me mention that this is a very simple theory, and actually there is a lot of debate now about going beyond this quasi-linear theory. This is just for you to know, but I will not go into the detail of that because this becomes very technical. But there is the discussion about the nonlinear feedback at low energy, below GeV in particular, or around GeV, and there is a lot of discussion about whether the Alfvén wave packets are actually the main responsible for cosmic ray confinement. This could not be true, especially way above the TeV energies. And the reason is that the turbulence cascade is far from being isotropic, according to the most updated and recognized models of turbulence. This would decrease the efficiency of Alfvén waves in scattering cosmic rays. And this would mean that other magnetohydrodynamic modes, for example, magnetosonic modes, in particular fast magnetosonic modes, may actually play a dominant role in the confinement. So there is actually the story is more complicated, as often happens, and there is an ongoing discussion whether about what is the nominal process at high energy for cosmic ray confinement. Maybe there is
a question, Daniel.
Yeah, let's see.
Can you read it, or do you want I read it for you?
Yes. Okay. Yeah, it's about the relation between the Larmor radius and the coherent length. Oh yes, that's very important. So, well, okay, so let's put some numbers here. So the coherence length is pretty large. So it's orders of tens or hundreds of parsec. So yes, all this theory, okay, all the scales of interest for our theory in this context happen way below this coherence length. So if you consider particles from GeV up to PeV, actually, they cover. They are sensitive to perturbations from astronomical units to parsec, let's say unit of parsec. So yes, we always fulfill the condition that RL is lower or much lower than the coherence length. Yeah, that's the. But yeah, it's very important to compare those numbers to understand what's going on. Okay, and yeah, so let me mention a little bit the full story now. So this is a very basic theory, but what do we do in practice when we want to model cosmic ray transport? So as for example, Gabi mentioned and other speakers mentioned, there is actually a very complex phenomenological equation that is usually solved, which does not imply diffusion only, but implies many other processes. So, yeah, sorry, let me close the chat otherwise. Okay, and so typically what we do is when we model the diffusion of production diffusion of cosmic rays in the galaxy, we solve this complicated differential equation that has typically source term, which should capture the acceleration of particles, for example, from supernova remnants, from pulsars, or from some exotic source, for example, dark matter annihilation or decay. And then we evolve this differential equation, and we solve this differential equation where we have a diffusion term, but we also have energy loss term, and we have terms describing a decay of unstable species, fragmentation of heavier species into lighter species, and so the full picture includes all these processes. The main ingredient is diffusion, because that's the main ingredient that shapes the spectrum of particles, but still there are all these processes to take into account, and this is taken into account typically numerically with global solvers that also Gabi mentioned, like Galprop, Dragon, Picard, also semi-analytical packages like Usin, and yeah, there are many tools. Today in the afternoon, actually in Gathertown, Pedro and Ottavio will show you, for example, how Dragon works and for solving this equation, and how Hermes is able to compute the associated gamma ray and radiation. So you'll see more about the solvers for this equation and the associated non-thermal emission in the afternoon in the hands-on session, which will be on Gathertown with Pedro and Ottavio. And yeah, let me mention that diffusion is the key process. And actually, in general, you see diffusion should be described by actual diffusion tensor, because I mean, quasi-linear theory predicts a diffusion that is mainly parallel with respect to the magnetic field, but in reality, again, the reality is more complicated. We have also perpendicular transport. So in full generality, we should take into account a full diffusion tensor with a parallel and perpendicular component with respect to the regular coherent magnetic field. This is very difficult to do. So typically there is the standard assumption instead that the diffusion coefficient is a scalar, and this is the way the typical assumption that is below many solvers of and many global fitting machineries for cosmic ray species. And I mean, there is a lot of there are a lot of tricky issues, but they work very well. So if you solve this equation for all species and you tune the relevant free parameters to the data, you typically end up with a very good description of all observables. So all the spectra and the secondary over primary ratios and so on. And in particular, let me mention one thing about, I mean, this could be very long, but let me just flash you one key concept in order not to give too much of information, that again about the diffusion coefficient. So this is very important. So I mentioned you a theory, right? A theory for the diffusion coefficient, a theory that predicts an expression for the diffusion coefficient as a function of the turbulent power. But what people typically do is not to use this first principle expression, because actually we don't know so much about turbulence. So that's a very useful guideline, as a useful theory. But typically we adopt to start when we study the real data a phenomenological approach, which is, okay, I parameterize the problem. I parameterize my diffusion coefficient as a power law in momentum, actually, with this expression d proportional to some momentum to some power of delta, and okay, this is inspired by quasi-linear theory, but eventually what we do is parameterize the problem and fit this delta parameter to the data. So there is a non-trivial interplay between theory and phenomenology here. So you have a simple theory as a guideline, but you remember this theory, but then you parameterize the problem and you fit the relevant parameters to the data. And this is because we don't have, I mean, the problem of turbulence is too complicated to actually directly match a first principle theory to real data. There are some attempts now in the literature, but actually we are working actively on that. But typically, what people do is really parameterize this problem in these terms. And yeah, let me flash just a little bit more about the effect of diffusion on the spectra of particles. And yeah, there is a very simple way to show this. So that very complicated diffusion equation can actually be written in a very simple way, in this way. This is the so-called leaky box equation, where basically the derivative of the number of particles with respect to time is proportional to a source term and to an escape term. So it's a balance between injection in the interstellar medium and escape from the galaxy. And this escape time is basically inversely proportional to the diffusion coefficient. So the faster the cosmic ray diffuse out of the galaxy, the lower the escape time is. So if the diffusion coefficient scales as a power law in momentum, the escape time will scale as p to the minus delta. And this is a very simple equation. Actually, if you model the source term again as a power law, as diffusive shock acceleration theory tells us, so if you assume that the particles are injected with a power law in momentum with some slope alpha, so Q primary is proportional to p to the minus alpha, then the stationary solution to this equation, to this differential equation, is n primary of p proportional to p to the minus alpha minus delta. So if you start from an injection spectrum of p to the minus alpha, the effect of diffusion is to steepen the spectrum by a p to the delta factor, basically. So the delta parameter, which describes the scaling of the diffusion coefficient with respect to momentum, gives you the amount of steepening. So the propagated spectrum of primary species is actually the original spectrum, p to the minus alpha, further steepened, and so eventually you end up with p to the minus alpha minus delta. And this is for primaries. For secondaries, actually, you already start, okay, the source of secondaries are, if you want, the propagated primaries. So you already start with the injection spectrum that is already steepened, is already p raised to the minus alpha minus delta. And then you produce secondaries. If you assume that the cross-section doesn't depend too much on momentum, then you end up with a secondary flux that is further steepened. So for the secondaries, you have the initial p to the minus alpha steepened twice, right? Because the first steepening is in the primary spectrum, and the second steepening is due to the further diffusion of secondaries in the galaxy. So eventually, the nice feature of this, the nice properties, is that the secondary over primary ratio scales as p to the minus delta. So if you consider a ratio between a secondary and the primary, its slope it will really tell you something about the scaling of the diffusion coefficient with momentum. So for example, a very widely used ratio is the secondary over primary ratio boron over carbon, and the slope of this well-measured ratio tells you something about the delta. So the scaling of the diffusion coefficient with momentum. And this is something you will see in the hands-on session. So there will be a small computation about this in the hands-on session. And yeah, let me mention very quickly, but I think this was covered a lot in this school, that there are several processes associated to cosmic rays that are mainly inverse Compton scattering, Bremsstrahlung, and pion production decay that give rise to gamma rays. So of course, this random walk of cosmic rays in the galaxy is typically associated with a very high energy gamma ray emission that the other speakers have described very well already. So I will not repeat too many details about this. Instead, let me go back to dark matter searches. I think there's still some time. So we'll be back go back to the original topic. So we want to understand how all this physics relates to dark matter searches. So to indirect dark matter searches. And so, I mean, these particles are really interesting to study on their own, but are also background for this kind of search. So let's see how this works. So the game here, as for example, other speakers already mentioned, is to look for anomalies. So you really want to study anomalies with respect to the basic picture described above. So you have these nice solvers, you predict your fluxes, and you compare your fluxes to the data, and you want to check if there are some excesses, for example, in some channels with respect to the background and to the naive expectations, let's say. It's not an easy task. And first of all, the first question is, okay, but which anomalies are we interested in? So which are the channels that we are mostly interested in? For example, what about if we have some anomaly in the proton spectrum? So for example, we have an anomaly, actually we have a hardening of the proton spectrum at 1 TeV. So could it be somehow related to dark matter or not? Is this a good channel? So are protons a good channel to look at? I mean, we have an anomaly in protons. We have a hardening. On the other hand, we have anomalies, for example, in antiparticles. So, for example, in the positron flux, that in the positron fraction, so the ratio between positrons and the full lepton spectrum, you have a significant anomaly. You have a steep rise at high energy, which is not predicted by any model of secondary positron emission. In the antiprotons, we start to check if there are some spectral bumps potentially associated with something exotic going on. So there are anomalies in many channels. So what are the ones that are interesting for dark matter searches? This is, yeah, I think a very important question, and the answer is again in the can be elegantly derived with orders of magnitude estimates. So I think it's very useful to work out these numbers. Again, this is a very nice exercise that you can do by yourself, really working out the numbers. But I think it's very useful to compare, on the one hand, the total power injected by dark matter in the interstellar medium if it annihilates into standard model particles, and this can be written in this expression, right? So the total power will be proportional to the density squared of the dark matter, of course, because it's an annihilation process. So as mentioned many times, you are sensitive to the square of the density of the dark matter flux, of course, integrated, for example, along the line of sight or along a path. And what you get, okay, when you work out the numbers about the total power injected by dark matter into standard model particles, and you compare it with the total luminosity or the total flux associated to cosmic rays in the galaxy, you see that this is pretty small. So you can work out a total luminosity, a total power associated to cosmic rays of the order of 10 to the 41 erg per second. It's a huge number, and dark matter can provide few orders of magnitude less. So this tells you that, for example, studying the protons is not so useful because, I mean, the proton spectrum is really dominating the flux, right? So this 10 to the 41 erg per second of total flux is really stored mainly in protons. So, I mean, any bump, any spectral bump, any feature in the proton spectrum, I think can be hardly interpreted in terms of dark matter. Actually, there are many astrophysical ideas and ideas connected to the physics of transport, and that I will not cover here, that can explain these features in the proton spectrum. But on the other hand, the antiparticles fluxes, since they are really 3-4 orders of magnitude lower than the proton flux, so the energy stored in antiparticles is very low. These are really relevant. So this is in the correct ballpark. So this is very interesting, right? So the antiprotons and the positrons are produced in a very small amount by the processes of proton spallation, and interestingly, the energy stored in this particle, in these antiparticles, is in the same ballpark as the energy budget that is potentially associated to indirect dark matter, to the flux and to the annihilation of dark matter, of WIMP dark matter into standard model particles. So that's interesting, and that's why there's been so much interest in any anomaly associated to antiparticles, namely to positrons and antiprotons, which are the ones that are most the most studied ones. And the reason is that, for example, other anti-nuclei, heavier anti-nuclei like antideuteron, antihelium haven't been detected yet. I mean, there is some tentative claim, for example, for antihelium, but I mean, there's no such thing as a well-measured spectrum like we have for antiprotons and positrons. So the game is to look for anomalies in these fluxes, in these charged particle fluxes. And in some cases, these anomalies are there and they're macroscopic. I mean, for example, in the positron flux, I mean, there is a very clear feature in the positron fraction that is incompatible with the standard picture of positrons as particles produced out of just spallation from primary nuclei. In the antiproton channel, there's not at zeroth order, everything is fine. But if you go deep into the details and you start to do a best fit of your diffusion parameters, there are some papers that claim the presence of a signal that could potentially improve the fit of these particles. And as we will see, this is heavily under debate. So, but these are two different debates. So in the positron case, the anomaly is really there. And the question is it astrophysical or is it originated by dark matter? But there's clearly an anomaly. In the antiproton case, it's really a fine-tuning problem. It's a very small signal and so the debate is whether the anomaly is really there, so whether there is really an anomaly. So the question here is also anomaly with respect to what. But still, the game is, okay, look at antiparticle fluxes mostly, and because they are the most promising channels for dark matter searches, and try to understand if there are anomalies and if they can be interpreted in terms of dark matter signals. And yeah, that's that was the takeaway, the take-home message for this part. And so how do the exotic signals would look like? So what kind of signals would we expect from dark matter annihilation? So okay, this depends on the final state. So the matter particles can annihilate into a variety of channels. So they can annihilate, for example, into quark anti-quark pairs, or into gauge bosons, into W, into Z, or they, depending on the scenario, they can directly decay into leptons. So, for example, electron-positron pairs. So there's a variety of final channels. We don't really know. This depends on the particular model. And if one is agnostic about that, one should consider all possible annihilation channels. And if you have an hadronic channel, a quark anti-quark or a gauge boson final state, you end up with a hadronization process and the production of pions, both neutral and charged pions, which yield a quite large number of positrons, because you know, charged pions can annihilate into muons and neutrinos, and muons in turn annihilate into positrons and muonic neutrinos. So you end up with the neutrino flux, and you end up with a positron flux. So there are several ways to produce antiparticles with this annihilation channels. Of course, if the annihilation is purely leptonic, then you directly have positrons in the final state, because you really have an electron-positron pair, or you have a tau-tau or a mu-mu leptonic final state, which in turn decay into positrons. So yeah, we have at our disposal some Monte Carlo simulators that allow us to compute the final state signal associated to positrons and to antiprotons, depending on the annihilation channel. And this was also discussed already in several lectures. So I will not go too much into the detail. Of course, you see the sharpness of the spectrum depend on the annihilation channel, and of course the steepest one, the hardest one, is the leptonic channel for the positron channel. But this was already discussed several times, so I will not go back into that. Let me also mention that with these annihilation processes, you can also produce gamma rays. And of course, you always have charged particles and gamma rays. And Gabi already covered the production, the possible detection of anomalies associated to gamma rays. And again, you have a gamma ray production from antimatter, from dark matter annihilation, both for as a consequence of the decay of pions, or as part of what is called final state radiation. So you can produce gamma rays, for example, because due to the process of internal Bremsstrahlung, which is described by this Feynman diagram here, when you just add a photon lag in your final state. So this is the internal Bremsstrahlung or final state radiation that could be responsible for gamma ray production. Or on the right side, you can see gamma rays also produced as a consequence of pion decay. So, I mean, we have well-defined ways to compute gamma ray signals, antiproton signals, positron signals associated to dark matter particles that can annihilate into standard model particles, depending on the final state, whether it is a gauge boson, a quark-antiquark pair, or a lepton-antilepton pair. And then the game is to understand if this signal is compatible with the data. So this is probably the very last thing I will mention. I think I will probably finish a bit earlier than planned. So I mean, we can spend some time on these last slides. So I can tell you a little bit about both the antiproton anomaly and about the positron anomaly. So the antiproton anomaly is discussed in a number of papers, and it is basically what people realized is that if you perform a best fit of your antiproton spectrum assuming that it originates from secondary interactions, so it originates from basically spallation of protons, and you do the best fit of your propagation parameter within one of these global framework that I told you before. So you have to solve your global transport equation, including energy losses, including all the processes that are of interest, and you best fit your diffusion parameter and all the other three parameters to the data. You end up with some residual, with some residual at energies that are slightly larger than 10 GeV that could be nicely fit by a contribution from dark matter particles annihilating into for example, BB bar or other channels with a cross section that is not so different than the one associated to another anomaly. So the one in gamma rays that Gabi talked about. So the galactic center excess or the inner galaxy excess in gamma rays. So this is a nice situation, because I mean, indirect searches are so difficult that it's very nice to have different claims in different channels that converge towards same region of the parameter space. The problem is that in this case, I mean, the claim is very difficult to do, because antiprotons are affected by a lot of uncertainties, and actually, if you go through the uncertainties associated to all the different aspects of the problem. So if you quantify the uncertainties due to the propagation, so the uncertainties that affect your estimation of the diffusion coefficient when you fit it to the data, the uncertainties in the primary slopes that are not big but are there, the uncertainties due to solar modulation, which is a process that affects the cosmic rays at low energy and due to the interaction with the heliosphere. And of course, also the uncertainties that are very relevant due to the production of secondary cosmic rays due to spallation that comes with unavoidable uncertainty. I mean, there is a way to, there are ways to quantify all these uncertainties. Typically one can perform Bayesian analysis for this and estimate the uncertainties on your secondary fluxes due to all these processes. But what you find is that this particular anomaly in the antiprotons is particularly under debate. So my take on that is it is very difficult to claim that there's dark matter here annihilating into antiprotons. And the take-home message from this anomaly, from the study of this anomaly, is really that, I mean, the cosmic ray physics plays a role when the anomaly is very small, is very tiny, and the uncertainties associated. You see, I try to convince you how complicated the whole process is. So you have a very complex equation describing cosmic ray transport. You have uncertainties in the diffusion. We don't even have a very precise theory of diffusion. We have some theoretical guidelines, but then you have to parameterize the problem and tune it to the data, and this tuning process comes with unavoidable uncertainties. On top of that, we have uncertainties on the spallation process, so it's all very complicated, and it's very hard when you have a very when you have a small signal to really make a claim. So the direction here is really to collect as many claims as possible in as many clean channels as possible, and ideally, if they all merge together and point towards the same region of the parameter space, that would be great. For example, it would be great if there were a signal from a dwarf galaxy potentially compatible with this signal. In that case, this would be really more convincing. But this is my take, of course, on the subject. And let me tell you that this is something that is really domain of current research. So this is under debate, and there's no universal agreement on these topics on whether this or that claim is interpreted in terms of dark matter. So this is something that I don't even want to bias you too much. I mean, these are anomalies that are debated right now in the literature, and I just want to provide you an idea of how complicated it is to make a claim of dark matter detection. Yeah, and then another case study, probably the last, is the one about positrons. And here, there's no question about the anomaly. So the anomaly is there. If you compute your positron fraction, so the ratio of positrons to electrons plus positrons, associated to a scenario where positrons are all secondary, so they are all produced only by spallation, then there's no doubt that there is a huge excess of positrons above 10 GeV. And there's also no doubt that this can be fit within a dark matter scenario. The challenges here are in the model building, because you have to explain, first of all, a very large annihilation cross-section into positrons. So boosted one, a couple of orders of magnitude more with respect to the thermal cross-section. And then you have to combine this claim with constraints coming from other channels. So you have to make sure that your specific model of dark matter, your specific mass and annihilation channel, or your more evoluted and complicated model does comply with all the other constraints. For example, here in particular, there are some CMB constraints that have to be taken into account, constraints from cosmological channels that have to be taken into account. So it's very tough for model building. It's also, this is an anomaly present only in leptons. So you have to, somehow assume that the dark matter particle has some leptophilic properties. So it may annihilate into leptons, into some mu pair, tau, or it's not the most natural thing you can imagine within the most widely considered extension of the standard model. So there are quite some challenges here. And here the main debate is, so it's not about whether there is an anomaly or not, but whether the anomaly is completely, possible to explain with astrophysics. So that's another typical discussion that is typically going on in the literature in this kind of case. So when there is a macroscopic anomaly, but you have, on the one hand, a complicated way to interpret it in terms of dark matter annihilation, On the other hand, you have an astrophysical way to interpret this anomaly. In this case, the way is to consider pulsar wind nebula. So as I told you at the very beginning, we have this supernova paradigm. So we believe that most of the cosmic rays are actually produced in supernova explosions. But I also mentioned that other sources might be at work, and in particular for leptons. So for lepton particles, the pulsars are a great environment for leptonic acceleration, and the pulsar wind nebula in particular is expected to produce via an electromagnetic cascade electron-positron pairs. So this is something that is unavoidable. Also, the energy, again, so there are complicated theory about how this acceleration can take place, but there is also a very nice and simple energy budget argument. So if you consider the energy associated to a few nearby pulsars that are very well studied, very well known, such as, for example, Monogam or Geminga, assuming a reasonable efficiency in leptonic acceleration, I mean, it's quite natural to believe that this high flux of positrons at high energy from 100 to GeV to 1 TeV can be associated and can be easily associated to nearby pulsars. So there are many attempts in the literature to fit this positron flux with scenarios where with one or few nearby pulsars, or a combination of few nearby pulsars and many faraway pulsars, depending on the energy range. And this interpretation is also corroborated by the recent report by Hawke of a bright diffuse TeV halo around nearby pulsars such as Geminga that is naturally interpreted as an outgoing flux of leptons that emit inverse Compton and produce this bright emission. So we now have also smoking guns of ongoing of an existing flux, of an outgoing flux of leptons out of nearby pulsars. So there are many reasons to believe that this interpretation makes sense, but still the debate is open. I mean, we don't have it's very hard to have the so-called smoking gun because as I mentioned, the cosmic particles do not point directly to sources. So the angular information is completely erased by diffusion. What could be left is some mild anisotropy towards some source. So it's still very interesting to measure with even more and more accuracy the level of isotropy of the leptonic charged cosmic rays, and to understand whether they point towards some nearby pulsar. But still, I mean, the final word has not been said yet. So we still have this, on the one hand, this dark matter interpretation, which has some complications due to the aspects of model building, to the large annihilation cross-section required, to the strong constraints, and to the leptophilic nature of this anomaly. On the other hand, we have a very reasonable scenario in terms of energy budget, and we have a very reasonable candidate as electron plus positron accelerator. But still, it's not super easy to really pinpoint at a very specific pulsar because of these complications due to the transport that completely erased the memory of the location of the source. So yeah, that was all. I think it was a long tour, and yeah, we have some time for questions if you want. Otherwise we can go.
Thank you very much, Daniele. This very clear lesson, a very complex topic. So questions? No questions for Daniele?
We'll also be on Guttertown, and then in the afternoon, I mean, there will be a hands-on session very connected to this topic. So there will be a description about how Dragon and Hermes work, and Pedro, Ottavio, and I, that we will be on Guttertown. So if for any question, you can directly contact me. Also later on, also after the hands-on session, we will be around in other town, either in the class or at the bar. I mean, we don't know, but somewhere.
So if there is no question, maybe I can stop the live stream.